Greetings all and welcome to a new video about another electric circuit example. We continue with the mesh current method, and that's where we are example number 3. In example number 1 and 2 we have seen only voltage sources, DC voltage sources, and a couple of resistors around it. In this case I would like to discuss a situation where we have a current source also. That will be also interesting, and also see what kind of effect this has in our analysis. Of course, we will work out the calculation step by step as we did in the previous videos, and also verify these in simulations using SPICE. Okay, this is the circuit we have given. There are 4 resistors, R1, R2, R3, and R4. The values are shown here. We have 2 independent DC sources. IS is the DC current source, 2 amps, and also VM is the DC voltage source, which is 10 volts. Now we like to calculate using mesh current method the currents I2 and I4 and the power delivered by this DC current source IS. The I2 and I4 in this tutorial video is oriented or chosen as this form, so going from the top to bottom for R2. And for R4 it is going from left to right as shown here. So we have 2 currents for question A, and question B is the power delivered by this source IS. Okay, so let's look at our solution step by step. We start first with choosing the loop direction. So first recognize, of course, the loops and then choose the loop directions. And this is really your own choice. If you make the choice in a different way, you will get exact same results. What do I have? I have actually a loop here, and another loop here, so second loop, and a third loop is actually here. So if I now say this is the first loop and I say that is the loop current IX, you need to assign also a loop current to that, and I will also name it differently. I don't name it I2 because that's already reserved for the resistor R2. We have also this loop, which is, let's say, IY, in a different name, and we have also another loop here, which is IZ. And that is a third loop. So if I now say loop X, if I look at it, something is actually interesting here, because this current loop, only considering this and just forget about the rest, is actually already IS, because in that loop the IS is setting this current IX. So we can say IX is equal to IS, and that is actually already done, so you don't have to set up the equations using actually Kirchhoff voltage law for R1 and R2, etc. So this is much easier now. So having a current source actually in your circuit, and you would like to use mesh current method, it is much easier. So for loop Y, we can now do a similar thing we have done in the previous videos. We can say, okay, R2 and R3, we need to add them together. And the IY is the orientation we have chosen clockwise. IX is actually fighting back for the R2, and IZ is fighting back for R3. So we have, in order, X, Y, and Z. You can say minus R2, because minus is because it's fighting actually back. It's the opposite direction of the current flow for IY, times IX, the summation of the R2 and R3, times the IY, but then plus, of course, that is our orientation we have chosen for this loop. And we have minus R3 times IZ, because that is also fighting back, so it's in the opposite direction. And we have the voltage source from the top to bottom, which is then plus, minus, and you get plus VM. That all adds up to 0. Okay, loop Z. In a similar form, we see R1, R3, and R4 all have the IZ as the positive orientation, but IX will fight back in the R1 resistor, and IY will fight back in the R3 resistor. So if I set it up again in order, X, Y, and Z, and there is no actually a voltage source or current source, anything here in this loop, so I only have resistors and the current equal to 0. So you will get minus R1 times IX, and a minus R3 times IY, and then plus the summation of R1, R3, and R4 times IZ and it all adds up to 0. Okay, that's now for the step 1, choosing your loop directions and also setting up this equation symbolically. Now we need to rewrite this equation and then for each loop, and then substitute the values given for this example. Now for loop x is quite easy because this is already given 2 amps, so Ix is 2 amps. So we need to only calculate I1 and Iz actually. So that's really easy now. It looks like we have 3 unknowns, but it's actually just 2 unknowns. Okay, we'll call that equation number 1. Loop y, that's this. So you actually substitute in this equation everything you see. Now it is now R2 is 40, R2 plus R3 is 40 plus 80 is 120, this is 80 and the rest is 10, so Vm, this is this. Okay, now we can place this 10 to the right hand side, so we will like to keep the variables left and the constants, the numbers, let's say on the right side. This is just the order. Then we have this, you can divide now by 10, you will get minus 4 plus 12 minus 8 is equal to minus 1. So everything is now nicely in order. Let's call this also equation number 2. Now going to loop Z, the final one, you can see the R1, R3 and the summation of these 3 resistors. These are here, so minus 20 Ix minus 80 Iy and plus 200 Iz is equal to 0. I can again divide this by, in this case, 20. I will get minus x minus Ix minus 4 Iy and plus 10 Iz is equal to 0. Now let's also call this equation number 3. Okay, what do we have now? We have one unknown already determined, and we have still the Iy and Iz to know. But I can substitute this Ix in equation number 2 and 3. So let's do that. Ix is 2 amps, and then substitute that in equation number 2 and 3, then we get the following. So I get 4 times 2, so minus 4 times 2, minus 8, and the rest is just copy. And for the next one, here is minus 2, and the rest is again copying. Now if I now place this minus 8 to the right hand side, you will get a plus 8, there will be then plus 7, so 12 Iy minus 8 Iz 7. In the symbol for I place the minus to the right hand side will be a plus 2, and I will get this. Now I will now collect these 2 equations number 4 and 5 also in the third step, I must say, for solving the unknowns. So bring them together and also give them a color. Let's say the Iy is the blue and Iz is the green and Ix is the pink one, so we can recognize this easily for the future steps. So in order to calculate this, there are many methods. I think the straightforward one is just choose for yourself the variable you want to make, let's say, have the same coefficient. You can see is a 12 here and a minus 4, and here minus 8 and a 10. You can try to make this, let's say, 80 or minus 80, and this is also 80. So multiply this by 8 and this, this by 10, this by 8. Or you can say I will want to choose a smaller value. You can say keep this equation number, this one in the top as it is, just multiply this by 3. I will do that, so I will keep that, but I will just multiply this by 3. There will be then minus 12 Iy plus 30 Iz, and then is equal to 6. That's actually just the result. Now add them up, and then you will lose this, because that will be then 0 times Iy, and you will get here minus 8 plus 30. For the Iz will be then 22 Iz, and 7 plus 6 will be then 13. Now you will get this, and Iz will be then 13 over 22. That's just approximately 591 milliamps, or 0.591 amps. So we have also Iz. Now we can now choose this equation or that equation to calculate the Iy, which is the final one. So I will now just select one. I think I will take this. Now we know the Iz, and we need to have the Iy. Now let's then express Iy in the rest of the parameters. So it means then 2 minus 10 Iz, and then divide by minus 4, and you will get Iy directly. Now we know this. If you substitute this here, exact value, for example, you will get 43 over 44, and that will be approximately 0.977 amps or 977 milliamps. Now we have now Ix, Iy, and Iz. All three are known. So let's collect them together here. 2 amps, 0.977 amps for the Y, and for the Z, the 0.591 amps. What we wanted, of course, was I2 and I4 and also the power delivered by this current source Is. So then we need to check in our circuit what it means. The I2 means actually it is Ix minus Iy. Look at the orientation, it goes actually in this direction. Ix is flowing in the same direction as I2, but Iy is flowing in the opposite direction. That means the following: for current I2, I need to say Ix minus Iy, which is then 2 minus this exact value, 43 over 44. That will give you 45 over 44 approximately. Will that be 1.02 amps? That's for current I2. In a similar form, I look at I4, but that is easier because it's already Iz. So for current I4, I can say that's just Iz and just copy this 0.591 amps. Okay, now that's question A. Let's now look at question B, power delivered by the DC current source Is. Now for the current source, I need the voltage in order to know the power. So the power is, of course, the current times the voltage. I know the current, but I don't know the I know the current, but I don't know the voltage across the terminals of these current source. So I need this Vs here, which is unknown yet. But it can be, of course, calculated, because we can say Vs is equal to the voltage across this node, so A and the ground, or between the A and the B plus Vm. That is again voltage law of Kirchhoff. The Kirchhoff voltage law says Vs, this voltage, is the voltage across R4 plus the voltage across the Vm. Or you can say the voltage across the R1 plus the voltage across R2. Or you can say also this, voltage across R1 plus voltage across R3 plus the voltage across or the Vm itself. So we of course take the much easier one. Vm we already know, so we can say let's take that. And also voltage across R4 is also easily calculated using Ohm's law, because we know our I4 and R4 is also known. So we can say this is the the easiest option to calculate Vs. Now V4 is the voltage across R4, and R4 times the current through it using Ohm's law. So current times the resistor will give you that voltage. What is I4? That's shown here, 0.591. What is R4? It is shown here, 100. So let's then multiply that. You will get 59.1 volts. We know Vm is 10, so we can say then Vs will be then 59.1 plus 10 will be then 69.1 volts. So we know now what we needed to know to calculate the PS, the power delivered by the current source Is. Then we get the following: 2 times 69.1, and it will be then 138.2 watts. Okay, now we have the calculations done. Let's now check the simulations, but before we move on in the actual simulator, I will show you the circuit. This is the circuit we will discuss shortly in the actual simulator. And this is the result, the table of result in a DC analysis. What you see directly is the following. We have Ix, which is 2 amps, that's here. We see that we have for I2 is 1.02 amps. That's actually this current going actually from node 3 to node 0. That's actually shown here. So IR2, so I underscore R2, 3, 0 means actually from node 3 to 0. It is 1.023 amps. So very close to what we have here, of course, due to rounding off errors. We don't have the exact value. And this current from the node 2 to 1, which is actually shown here, so the current R4 is 590.909, which is approximately 591 milliamps, also what we have. So nice results. So they are confirming our calculations. Now let's also see that in action in the real simulator, and also produce this table also, and you can see how we do that. So let's jump to the simulator in SPICE. Now we are in the simulator, TINA TI SPICE. I have already prepared the circuit for you. We have the current source IS here, 2 amps. We have the voltage source VM, 10 volts, and all the resistors we have in our exercise, in our example here. Now what we have done was show the table, so let's also generate that using analysis and DC analysis, and then table of results. Now this will then pop up, and that is actually the table. What we now can see, we can highlight the current where we want it. So if I now go with my pen here and I click on this R2, I can highlight this. You will see two things will be let's say red. That's the current to R2 and also the volts across it. You can also, for example, do it here. That's for the R4, and you see also 591 milliamps. Again, exactly what, very close to what we have calculated. What you also see is the following. This voltage here at this node is 69 approximately 1 volts. Exactly, actually, very close to what we have, I should say, what we have calculated in order to calculate the power delivered by this current source IS. So that is really nice to see also here. You can also, of course, check this node or that node. That is, of course, just 10 volts. You can also see the currents for the others. So that is really handy to see this in the simulator. All right, guys, this was our third example about the mesh current method in electric circuits, in the DC domain specifically. I will move on and make this situation, try to make the situation even more clear using a number of other examples. Of course, we also have other videos in the pipeline using node voltage analysis and a third position, Thevenin, Norton, etc. So that will be all coming in the coming days, and so stay tuned. And if you have any questions, comments, please let me know. I will try to answer them as soon as possible. See you next time in another interesting video. Take care.